I have two talks in the succession by Matt Nicholl and Ryan Chernow.
Okay, thanks Brian. And thank you for organizing this meeting before any of us had a chance to catch up on sleep. It's the first Saturday since it became public. All right. So you've seen some of this already in Brad's talk this morning. I'm going to talk about the optical counterpart. Ryan's going to focus more on the infrared part of the same counterpart. So the images shown here are the optical discovery from our team that used the dark energy camera on the 4-meter Blanco telescope. So many groups discovered this, as you heard. The Swift group announced it first, and then like 5 other groups within an hour had also seen and announced this thing. I haven't had time to read most of those papers, so I'm going to show you a lot of stuff from the DECAM team. So the one thing that makes DECAM different from the other survey that did this, most of the others with small telescopes image all the big galaxies in the region. We actually tried to cover the whole LIGO probability area. So the white contours are the LIGO area, and the red sort of hexagons are the images we took with DECAM. So initially we covered the full 90% probability region. Afterwards the LIGO area shifted slightly. We ended up with about 80%. But that still turned out to be pretty important because we want to be, we know this is the counterpart to the LIGO source, but let's be pessimistic for a second and say, how do we know there wasn't another counterpart somewhere in the field? It turned out there were 1,500 candidates across the DECAM region we looked at, but we applied a series of cuts. First of all, it had to be detected in 2 different filters, I and Z. We also did a machine learning algorithm for rejection of image subtraction defects. And finally, we need something that faded much quicker than a supernova. So 14 days after the merger, this optical signal is completely gone. And in fact, this was the only source in the field that matched all 3 of those criteria. So we are actually pretty confident that this was the real deal. But even had we not done this rigorously, I think when we saw the fairly unique properties of this transient, we still would have been pretty convinced that this was the kilonova. So here are our light curves from the dark energy camera. So after we found the first night, we started imaging in every optical filter from the U-band through the GRIZ and even the near-infrared Y-band. And the light curves look something like this. So this the y-axis range covers about a factor of 250 in luminosity. So you can see that in the bluer bands, it drops by several orders of magnitude within just a couple of days. It's a really incredibly fast decline in the blue. And it lives a little bit longer in the near-infrared and the red or optical bands. You can see that it fades by about the same amount in a time of around 2 weeks. So unfortunately, after about 2 weeks, it became pretty sun constrained. It was setting very quickly at the start of the night, so this was about as long as we could follow it. There are a few more data points in the infrared with some other telescopes, but this is kind of the full duration that most groups were able to observe this thing for. But I think the really striking thing is the fast fading in the blue compared to in the reds. And here's the same thing in movie form for PR purposes. So you can see as the counter goes up to like 10 days, the optical flux drops off extremely fast. And as I mentioned, we did this with a dark energy camera, but we were not the only ones. So here's where I give everyone else a plug. This is now the Open Kilonova catalog, which is launched within seconds of its becoming public. And there are now, I think, 600 individual photometric measurements of this thing, so a really incredible data set. 600 images in 2 weeks, which is obviously a lot of redundancy here, but for modeling efforts, that's going to be pretty fantastic. You can see how many filters here, all the optical, you've got the HST, and the near-infrared. So all that data is publicly available. Here is the plot that I think is legally obliged that we show the Metzger-Berger diagram, the different components. How are we sure that what we saw in the optical is really the kilonova? Because hypothetically there's also the GRB afterglow that could be contributing to the optical. And in fact, as we'll see, that the kilonova was much bluer than we expected. So then even your bluest models are still struggling in this one, I think. But we've kind of answered this question already. So as Raf showed this morning, if you model an afterglow that can match the X-ray and radio properties, you find that the optical flux is many orders of magnitude fainter than what we actually measure. So I think, I'm not sure about cocoon emission models, but certainly for an off-axis afterglow, it should not in any way cause problems for our optical observations of the kilonova. And being off-axis turns out to be really helpful. So there's this one sort of best case previous kilonova detection that we saw earlier, GRB 130603b. So this is our previous kilonova. It's one data point in the H-band near infrared. At earlier times, so these lines are kilonova models that kind of fit roughly to this data point. Up until sort of several days or even weeks after the merger, you're totally dominated by this GRB afterglow. But because for this case we're well off axis, you don't have to worry about this contributing and drawing out your optical flux. So we've gone from this one data point to something more like this, and plus 550 more data points. So it's a huge boost. We can now finally actually apply some kilonova models in detail and see how well we can do to match these observations. So that's what we did. So the big thing about these kilonovae beforehand is, as we've heard, the observations are very sensitive to the opacities, both in the duration of the light curve and what colors you get. This red versus blue kilonova problem that Brian talked about years ago. So we applied a range of kilonova models for different assumptions about the opacity to try and kind of rule out different parts of this parameter space. So the first thing we tried is this iron kilonova, which is I'm not sure anyone actually thinks theoretically this is what will happen, but it's useful to sort of rule out a supernova. So this model is fit to the data with our MC light curve fitting code MOSFET. It does make some simplifying assumptions. We assume a black body, which is not a great assumption, it turns out. But it's essentially an RNet model. You got radioactive heating, you got diffusion through some kind of photosphere, and then ejected that expands with time. So if we assume an opacity similar to what we use for supernovae, about 0.1 centimeter squared per gram, and the heating rate consistent with the decay of radioactive nickel, these are the light curve fits you get. So it does kind of okay in some of the bluer optical bands. It does pretty bad in infrared, and it needs to be. I think that the mass comes out to actually be a few hundredths of a solar mass, so similar to what we've heard before. But most of that material would need to be nickel to make this work. So we're happy that it's not a supernova. That's a good start. Then we try the blue kilonova model. So for the blue kilonova, we keep the supernova opacity, but instead of nickel 56 decay, we use this R process heating rate. So this T to the minus 1.3 that we've heard about. In a similar way, the blue kilonova model doesn't do such a good job. So with just a blue kilonova, again, in the optical bands, you match the flux fairly well. You at least get this steep drop off and you get a bright peak. But it doesn't get anywhere close in the infrared. So these are, this K band over here does particularly badly. So blue kilonova by itself is not so great. What about a red kilonova? Even worse. So for the red kilonova, we assume a higher opacity. 10 centimeters squared per gram is roughly the gray opacity that you calculate using some of Dan Cason's opacities. In this case, in trying to match everything, it ends up matching nothing. So you can see clearly you got a much longer time scale when you get the high opacity model, but you can't get anywhere near this blue peak or the fast decay. So none of the single component kilonova models that we tried worked, but a two component kilonova actually worked very well. So for the two component, we've got essentially the two previous models that I showed. You've got one set of blue material with an opacity of order of 0.1 centimeter squared per gram, and a red component with a higher opacity. And for each of these, the velocity and masses are free parameters. And you can see that with two components, you can match both the blue early flux and the fast decline, and there's broader, slower behavior in the infrared bands that does much better at matching the observations. We've also got some zooms to individual bands. You can see the fast declining G band, and a much broader H band at the bottom. So the two components, it works much better. The parameters we actually infer for this are, in the blue, it's a few hundredths of a solar mass at a velocity of 0.3 c. So it's the same velocity we've heard mentioned many times today. And in the red, a slightly larger ejected mass, about 0.04 solar masses at a lower velocity of about 0.1 c.
So how many total number of parameters you use for this fit?
So you've got mass and velocity in the blue and the red is 4. I think we actually let the opacity vary in the red part, which is 5. We had to put some kind of temperature floor at the end to stop everything going optically thin. I think that turns into a free parameter. It's about 6 free parameters, I think.
The Kleistberg pretty great freedom is still better, isn't it?
Oh yeah, it's way better. Kleistberg pretty great freedom is way better.
So, I guess the other thing, or maybe you're going to mention this, but I mean, we do have evidence spectroscopically that
two components. Right?
Yes,
Maybe you're gonna say
I
that.
believe that's next slide.
Okay, sorry.
Yeah.
Sorry. Just so people don't stake too much on a leap of faith.
Yeah.
So it's going to come.
Yeah, no, the spectra, I think, really support what we find from the light curve. It works out pretty consistent. So, indeed, this is our next slide. So these are what our spectra look like. So we got optical spectra using SOAR and later Magellan as it got faint. We've got infrared spectra with Gemini that Ryan's going to talk about a lot more. Again, I will say that I'm showing our group spectra. There are many more spectra available, but ours are obviously the best. Our color scheme is not. I apologize, it's hard to see the yellow in the middle. This was more for public outreach than for a science talk. But I really haven't had time to make a second movie. Because it is a movie, I'll play it right now. So at 1.5 days, you've got a very broad blue peak at around 5,000 angstroms, but that blue flux disappears very quickly. And you can see in the infrared, if you can see that at all, the peak actually stays around for a lot longer. So the optical flux drops extremely rapidly compared to the infrared, where here we lose everything within sort of 4 or 5 days. In the infrared, it takes more like 10 days for that flux to drop. Everything will come back again, you can see a little bit more clearly. So yeah, Ryan will talk more about the infrared, but I think what's really striking is this like obvious divide at around 9,000 angstroms. You really have, I think, a very clear evidence from the spectrum to support the light curve that you've got these two components, and the one component fades a lot faster than the other. So I thought that was really nice. So let's look at the optical spectra again, slightly more easy on the eyes color scheme. So once again, you can see from 1.5 to 2.5 days, this incredibly fast drop in flux, and lots of other kind of weird features too. So, you know, what's really striking at the 2.5 and 3.5 days is this really sharp cutoff in blue wavelengths. This is, you know, there's nowhere of any other transients that have this kind of extremely sharp peak. So it moves from kind of 5,000 to 7,000 to 8,000 angstroms as this thing fades. And as I mentioned before, it doesn't really look anything like a black body. So this inset here shows black body fits to all of these spectra. So maybe in the very first day, you could kind of fit a black body. I know people fit black bodies to photometry and it worked okay. Even at 1.5 days, the spectrum started to deviate pretty far from a black body. And after that, this absorption is just completely inconsistent with a black body. So something more interesting is going on here, especially in blue wavelengths. We also got one spectrum with Hubble, which is essentially 0 photons, but I don't think as useful as RAP's 0 photons. It did cause a bit of a headache on Twitter when Hubble pointed at it, though. So it was fun. All right, so let's see. Yeah, all right. So just to hammer home this point about the spectra looking weird and very unlike any previous transients, here are some comparisons with supernova spectra. So the general physics between the kilonova and the supernova are thought to be similar. You've got some expanding material that's heated internally by radioactive decays. That energy is thermalized in the ejecta and kind of gradually diffuses out. But the spectra really look nothing like a supernova. So supernovae at maximum light are shown at the top panel. These have obvious resolved line features. We really don't see those at all in the kilonova. I think the most striking feature of the kilonova spectra are just that they're so featureless. You don't see any obvious line features. In the bottom panel, I've got a supernova shortly after explosion. So for the kilonova shortly after explosion and maximum brightness are the same thing. And here the striking difference is that the supernova is much closer to a black body compared to the kilonova. So I think this comparison highlights two things. So one is that in I think, hopefully a fairly model-independent way, the lack of resolved line features really adds weight to this idea we've got a high velocity, which is really important. And the other thing is that the huge deviation away from this kind of thermal continuum also highlights you've got some kind of more interesting physics and probably some very heavy absorption. And that heavy absorption will hopefully be explained through kind of this unusual composition of our process material. So we compared our spectra to some model spectra from Danny Kaysen, trying to explore these parameters a bit. Ryan will talk more about this, especially in the infrared. But what I want to highlight is that to get this featureless spectrum, once again, you really need the high velocity. So this bottom panel here shows the model spectrum as we vary the velocity. So at 0.1c, you can see obvious resolved line features. At 0.3c, you've got something very smooth. So I think this further adds to the sense of you need a high velocity to match the spectrum. And this velocity of 0.3c is the same velocity that we infer from the light curve, and the same velocity that people kind of guesstimated by fitting a black body in 1 day after the disruption. So I think the high velocities in the blue stuff seem pretty robust to me. To get the luminosity, sort of a few hundredths of a solar mass, so that's similar to what we find in the light curve, so that's good. The other panels show the effect of varying the composition. So the only thing I really want to highlight here is that to get this sharp cutoff compared to the black body, you can do that with absorption from lanthanides, but you need a small lanthanide fraction to kind of match the blue luminosity. If the lanthanide fraction gets too high, you push all the flux to the near infrared. So this suggests the blue stuff is coming from weak R process that doesn't have much lanthanides, but just enough lanthanides to give you kind of some cutoff compared to the black body. So we just heard a lot about the source of these different components, whether you get lanthanide rich or lanthanide per material, and what direction that comes out in. So I'll give my observers a quick summary of that. There are essentially 3 ways, I think, to get ejecta from the neutron star merger. In the equatorial plane, you've got this tidal ejection, which we think is sort of the red stuff. In the polar direction, you can get either shock ejecta from the collision of the neutron stars, or the wind ejecta from the accretion disk. And the big difference between that is that the shock ejecta, you can get velocities up to 0.3 c. For the wind ejecta, we think it's less than 0.1 c. So it's a pretty significant difference. And the fact that we see high velocities in the spectrum, in the blue component, I think are pretty indicative that we might be seeing the shocked ejecta rather than the disk wind. So there are some implications of that. Implication 1, so we heard this morning that LIGO by itself was unable to distinguish whether you had a merger of 2 neutron stars or a merger of a neutron star and a black hole. But actually, to get fast blue ejecta, this dynamical shocked ejecta, it really has to be the former. It's got to be 2 neutron stars. Because if you've got one's a black hole, there's no surfaces to collide here. So if you take these high velocities to argue for the shocked ejecta, you can actually discriminate between the 2 situations. So that's very useful information. Implication number 2, this has also come up a lot today, the viewing angle of the system. So if you're viewing this stuff side on, the red stuff's got a much higher opacity than the blue stuff. So it's very hard to see the blue ejecta from kind of viewing angles over here. To see the blue ejecta, we roughly estimate you need a viewing angle within 45 degrees of the orbital axis. There may be some caveats to that. If the blue stuff expands a lot faster than the red stuff, maybe you can see it from a wider range of angles. But actually this less than 45 degrees agrees pretty well with both the constraints for the gravitational wave signal and what we infer from the radio and the X-ray. So that sort of all holds together as a pretty consistent picture. Implication number 3, starting to get really speculative now. Depends on the neutron star radius and the equation of state. So in this scenario where the 2 neutron stars collide and eject the ejecta by the shock heating, the actual ejecta mass is most sensitive to the radius of the neutron star, simply because the more compact the neutron star is, the closer they can get together before they collide, and therefore they're moving more quickly and get a stronger shock. So again, theorists have said a lot more than me about how much mass you can get out. Maybe you actually can't get up to a few hundredths of a solar mass, or it's very difficult. But at least some simulations have shown a clear correlation with larger ejecta mass for a more compact neutron star. So again, the high velocities that we see in the blue component would argue in favor of more compact neutron stars, and maybe you can start to disfavor some of the equations of state to give a more massive neutron, or a more extended neutron star. So hopefully with many more of these systems, if we keep finding fast blue ejecta and a large massive blue ejecta, that can start to eat away at this allowed parameter space for the equation of state. Okay, so, and before I hand over to Ryan, I would like to talk a little bit about the optical observations of the host galaxy, because they also contain quite a lot of information about this system. So NGC 4993, a massive elliptical galaxy, the biggest galaxy in this part of the sky, which is why we were able to find this so quickly. Ryan saw the transit in this galaxy within about 5 minutes of downloading the images. So we went back and got some really nice Hubble images of this galaxy. And all I wanted to highlight here was that although it looks like a nice smooth light profile, it's actually got a lot of substructure you kind of fit and subtract off this density profile of the smooth part, you can find these nice dust lanes in the optical, and you can these concentric shells in the infrared. So that's sort of indicative of past mergers in this galaxy. We've also got the X-ray and radio data indicating a weak AGN. But what was really cool about this was that, first of all, in archival data, and second, from our Hubble images, we had a really nice measurement of the broadband spectral energy distribution of this galaxy. And fitting the galaxy with a model was able to really nicely constrain the star formation history, which helps to constrain the age of the merger. And it turned out that this was a really old and really dead galaxy. So we actually find an exponentially declining star formation rate. So we're T of 0 over here is today. The star formation peaked essentially way back in the beginning of the universe and been dropping ever since. And we find that 50% of the stars had already formed 11 giga-years ago.
How do you find the thickness of the disk?
So this actually makes this the oldest and deadest galaxy to ever host a short GRB.
I don't remember.
So these histograms just show the age of the stellar populations of previous short GRBs. NDC 4993 is over here, the oldest ages. And present day star formation rate, it's right over here at the lowest star formation rate. And that's really cool because you can convert this probability of system age into a probability of an initial binary separation. So the actual merger timescale is only really a function of separation and eccentricity. So if the system was between, I think we found it was between 13 and 7 billion years old. This blue band is the allowed binary separation of the neutron stars as a function of eccentricity. So for any kind of lowish eccentricity, less than kind of 0.8, we find that the initial separation is kind of a few, up to maybe 10 solar radii. Just slightly at the large end compared to these simulations. But the purple points here are galactic binary neutron stars. It's actually pretty consistent with those, so that was also pretty nice. Okay, so rushed a little bit to hand over to Ryan because I know everyone wants to hear about our process. But I will put up these conclusions. So first of all, only kilonova candidate in the field, good. Second, the data for this is not incredible. It's all publicly available, these 600 light curve data points over this 2-week period. I think both the light curve models and the spectra really support a 2-component kilonova. So you can see it in the spectrum, and you can only fit the light curves if you've got 2 separate components. So a fast blue component with the low opacity ejecta, which presumably is in the polar direction based on all the simulations we heard about, and a slower high opacity component that Ryan's going to tell us about. And the mass and velocity of the blue ejecta may, if we take them at face value, be very constraining for models of the system. So favors a neutron star binary rather than a neutron star black hole binary, which we could not tell from gravitational waves alone. Gives us a viewing angle sort of close to pole-long, which agrees with the gravitational waves and the radio data. And the high mass that we seem to get in the blue component would favor a soft neutron star equation of state. So that would be really fantastic information. I will say that there are probably many caveats to that. We don't fully understand this blue component. I'm sure there's other models that can produce it. But comparing our observations to simple kilonova theory seems to work remarkably well and probably has some important implications. So I'll stop there. Thank you.
Questions for Matt? Zoltan.
Maybe
Ryan can come up.
In NGC 4993, this happened too late to at which the stars with our process formed. The galaxies are dead. So other short GRBs, do they happen? Do we know they're located in star-forming regions?
Short GRBs typically are not in star-forming regions or even star-forming galaxies. I think it's 25 or 30% of short GRBs are in star-forming galaxies. Most of them are in ellipticals.
The other way around. I think it's the other way around.
The other way around, yeah, sorry.
I think most,
It's a substantial fraction in dead galaxies.
Is there an issue of producing our process fast enough?
Not that I'm aware of, but I don't know.
You have, no, I think it's the other way around. So I think 60 or 70% are in star-forming galaxies. So I don't think it's an issue. But I think the main thing is they're not in the part of those galaxies where there's currently active star formation.
Yeah, so this one was actually a relatively small offset. Sometimes these mergers happen with at least the short GRVs, happen way outside the galaxy. This one happened, there's only 2 kiloparsecs offset, so that suggests that it's had 11 billion years to travel around this galaxy after the supernovae went off. So it must have got a pretty small kick, and it's actually stayed inside the galaxy potential well throughout that time.
Let's thank Matt again.
May have already been there.
Okay, so now we're going to hear from Ryan Sharnock about the infrared, maybe all the spectra. I don't know, maybe you're focusing on one, but